Welcome back, everyone, to our deep dive into the world of agentic systems. Today, we are opening the case file on one of the most critical components of our intelligence system, which is memory. Specifically, we are looking at memory systems for intelligent agents through the lens of a junior engineer agent. For too long, people have thought of large language models as simple text generators. But if we want to build a true partner, we cannot treat them as parrots that simply repeat what they have heard. We're engineering a partner that can handle complex multi-day tasks. This session is your guide to the architecture of short-term memory, long-term retrieval, and perhaps most importantly, the critical art of forgetting. We will explore how we move from basic context windows to sophisticated vector vaults. By the end of this video, you will understand how to build a cognitive architecture that allows an agent to reason, remember, and act within a professional environment, just like a human teammate would. Let us step into the office and begin our investigation into how machines truly remember. Our primary objective here is to move beyond the limitation of standard chatbots. We do not want a parrot, we want a cognitive teammate. Think of a junior engineer joined to your team. They need three essential capabilities to be useful. First, they must be able to track the current lead. This means following a discussion as it unfolds in real time without losing the thread of the conversation. Second, they must be able to remember old cases. This involves recalling past project decisions and data across days or even weeks. An agent that forgets what it did yesterday is not an effective partner. Third, they must be able to filter the noise. High level cognition requires knowing when to let go of relevant details so the important facts can shine through. There's currently a massive gap because humans naturally juggle short term conversation and long term knowledge using biological structure we have had for millions of years. For our agents, we have to rebuild this entire cognitive framework from scratch using code and infrastructure. This slide sets the stage for how we translate human like memory into a system of databases and logic. To build this cognition, we need a clear architectural blueprint. Imagine an office with three distinct areas. First, we have the desk, which represent the context window or short-term memory. This is like the random access memory of a computer where immediate work happens. It is fast, but very limited in space. Second, we have the file room, which represents vector databases or long-term memory. This is for permanent records that we do not need every second, but must be able to find when the situation calls for it. Third, we have the shredder, which represents management and forgetting. This keeps the office functional by removing clutter. We can look at the evolution in three phases. Phase 1 is the bare large language model utilizing the context window as its primary working space. Phase 2 moves into external memory where we add vector databases and retrieval augmented generation to simulate long-term retention. Finally, phase 3 is management, where we layer in mechanisms for forgetting to ensure scalability. The core analogy here is simple. The model is the brain of the context window, is the RAM, and the vector store is the knowledge base. Together, they form a complete cognitive office environment. Let us look closer at section 2.2.1, which covers the notebook or the context window as working memory. By definition, the context window is the maximum amount of text measured in tokens that the model can see and condition on in a single pass. Again, let me repeat that. The context window is the maximum amount of text measured in tokens that the model can see and condition on a single pass. You can think of it as the current page of a notebook. The composition of this notebook includes several key elements. It starts with a system prompt and code instructions followed by the conversation history, which usually consists of the last few turns. Then we inject retrieve documents that might be relevant to the task. And finally, We have a scratch pad for the agent's internal thought and reasoning. However, there is a hard rule you must remember. The large language model only remembers what fits inside the current prompt. Everything else is effectively invisible to it. This form of memory is ephemeral, meaning that when the session ends, the memory dies completely. Understanding this limitation is the very first step in realizing why we need more than just a large language context window to build a truly intelligent and persistent agentic partner. While the notebook is powerful, we must understand why it is not enough on its own. Imagine an engineer whose desk is so covered in papers that they cannot find their pen. This is what happens when we rely solely on the context window. First, there is a hard length limit. History instructions and documents all share a fixed token budget. Long investigations or complex tasks eventually force us to drop early clues which break the narrative arc of the agent's work. Second, we have the issue of cost and latency. More tokens equal higher inference cost and significantly lower response speeds. Enterprise system must keep prompts lean and responsive to remain viable. Third, and perhaps most subtly, is the problem of noise and interference. Blindly stuffing every piece of history into the prompt floods the model. Irrelevant context hurts performance due to the lost in the middle phenomena where the model ignores information buried in the center of a long prompt. This visual here shows an agent overwhelmed by paperwork, which is exactly what happens to an LLM when the notebook get out of control. We need a way to manage this flow efficiently. To manage short-term memory effectively, we use several distinct patterns to pack the last few minutes of interaction into our limited RAM. The first is the plain conversation buffer, which keeps all messages linearly. This provides high fidelity but zero scalability because it grows until it hits the limit. The second strategy is the sliding window. This keeps only the most recent set of messages. It focuses on local coherence, but major drawback is that the agent loses all distant references as soon as the slides out of the window. The third and most advanced strategy is the hybrid summary plus buffer approach. In this pattern, we maintain a running summary of older parts of the conversation while keeping the most recent messages verbatim. The result is that we compress distant context into a few sentences while preserving the high fidelity detail where the model is most sensitive, which is usually the last few turns. This hybrid approach allows the agent to remember the general gist of a long meeting while still being able to react precisely to the latest question. It is a vital pattern for any junior engineer agent trying to stay organized. Now we move into the section 2.2.2, which explores the archives or long-term memory. This represents a fundamental shift in our architecture. While short-term memory dies with a window, long-term memory persists in an external storage. The infrastructure required for this involves three steps. First is storage using vector databases to hold high-dimensional embeddings of data. Second is retrieval, which uses vector search or similarity searching to relevant pieces of information. Third is injection, where a prompting layer feeds the retrieved content back into the context window for the model to use. The ultimate goal here is to simulate infinite memory by decoupling storage from reasoning. In the bare model, reasoning and memory are fused together. But by using a vector database, we allow the brain to focus on the current task while the archives hold the vast library of experience. This allows a junior engineer agent to recall a project from 6 months ago just as easily as a human would by doing to the filing room and pulling the right folder. This persistence is what gives agent their long-term utility in the enterprise. The filing system of our archive is built on vectors and embedding through an indexing pipeline. This pipeline has three main stages. The first stage is chunking. This involves splitting raw content like logs or transcript into small manageable pieces, usually between 100 and 200 characters. This makes the data easier to process and retrieve. The second stage is embedding. Here we use an embedding model to convert each chunk into a high dimensional vector. This process essentially turns semantic meaning into a mathematical coordinates in a multi-dimensional space. The third stage is storage, where we save these vectors along with metadata such as ID values, timestamp, and source tags into the database. The core concept to grasp is that the vector database acts as a memory bank for the agent. It holds knowledge that exists far beyond the model's original training data. By turning text into coordinates, we enable the system to find information based on how similar two ideas are mathematically, which is the foundation of modern retrieval system. It is the digital equivalent of filing folders by topic rather than just by name. Now, let us walk through the retrieval process known as the retrieval augmented generation or popularly called as a RAG workflow. We can visualize this as a high-tech investigator and their faithful search dog. It starts with a query, where a user input is converted into a vector. Then the system performs a similarity search where it scans the vector database to find the nearest embedding, which we call as the top K results. Think of the mechanical dog finding the exact folder in a massive archive. Once the system finds the right chunks, it moves to the augmentation phase, where these retrieved pieces are inserted directly into the context window. Finally, the large language model generates an answer conditioned on both the original query and the newly retrieved context. The result of this four-step process is access to effectively unbounded knowledge. The agent does not have to know everything at once. It just has to know how to find the right information when asked. This workflow allows us to build agents that are always up to date with the latest company logs or project details without ever needing to retrain the underlying model. It is the most efficient way to give an agent a long term memory. But sometimes simple vector search is not enough. So we must go beyond and look for hybrid and graph retrieval. Hybrid retrieval combines vector search, which is based on a semantic similarity, with keyword search, like BM25, which is based on exact matches. This is crucial because it ensures we do not miss specific error codes or names that a vector search might overlook due to their unique mathematical signatures. On the other hand, we have graph-based retrieval. This models entities as nodes and their relationship as edges. For example, it allows the memory to capture structured relations such as stating the issue 1, 2, 3 as caused by update X. A vector search might find both items, but it would not necessarily understand the causal link between them. Graph retrieval uses heuristic algorithms to traverse these subgraphs instead of just retrieving isolated text chunks. You can see this visualized as a detective's board with a string connecting different photos and notes. By combining keywords, vectors, and graphs, we give our agent a much more robust and a nuanced way to explore its archive and find the truth behind complex technical problems. We now have come to section 2.2.3, which covers the cleanup and why forgetting is actually a feature of a smart system. It sounds like a paradox, but we must intentionally forget some things to remain smart. There are four primary reasons we must manage memory and use the shredder. First is unbounded growth. Without a cleanup process, index bloat leads to high latency and massive storage cost. Second is noise reduction. Keeping everything forever eventually dilutes the relevant context, making it harder for the agent to find a signal in the noise. Third is privacy and compliance. We must enforce data retention policies and protect user secret by shredding sensitive information after it is no longer needed. Fourth is adaptation. Making room for new learning is essential for what we call plasticity in AI system. Just as a human brain prunes old connections to learn new skills, an agentic system must discard the trivial to focus on the vital. Forgetting is not a failure of the system, it is a deliberate design choice that ensures the office stays functional and the agent stays sharp as its experience grows over time. To manage memory correctly, we look at axis of the management. Think of this as a funnel that processes raw logs and chat history into what we call as golden nuggets. The first axis is the capacity management. We must decide how much information is to keep by monitoring the total index size and the query latency. If the database gets too large, retrieval slowdowns for everyone. The second axis is relevance and prioritization. We have to decide what is worth keeping by assigning important scores to different memories. Critical decisions and project milestones receive high priority while casual chit chat is marked as discardable. The third axis is transformation. We ask in what form should the information be kept. This might involve summarizing repeated interaction and or consolidating raw logs into high-level semantic concepts. By transforming data as it moves through the funnel, or we reduce the storage footprint while increasing the value of each piece of information. The final result in the box at the bottom is a collection of golden nuggets of high-value knowledge that are ready for the agent to use. This management keeps the system lean and powerful. Let us discuss the operational mechanism we use for implementing forgetting in a live system. On the context level, we can drop the oldest messages or limit the number of top K retrieval results to keep the prompt clean. On the storage level, within the vector database, we have two main tools. First is time-based retention, or time to live, where we delete data automatically after a set number of days. Second is the use of decay curves, modeled on human cognition like the Abiogon's curve. This involves importance weighted decay, where valuable memories persist for a long time while trivial ones fade away quickly. Finally, we have adaptive mechanisms where we periodically reset parts of the memory to prevent catastrophic overload and support lifelong learning. You can see this visualized on the calendar where some days are crossed out and forgotten while a folder marked important is saved. This balance between automatic deletion and importance-based saving ensures that the agent's memory bank does not become a digital junk drawer. It mimics the natural human process of moving important facts to long-term storage while letting daily minutiae fade away into the background. Putting it all together, we see the full stack of a MAANG-level architecture. We have the user interacting with the agent in the precinct. The agent manages its context window for short-term memory to maintain local coherence on the immediate task. The agent is constantly communicating with the vector database archives to retrieve and store persistent knowledge across sessions. However, there is a third crucial player here, which is the manager overseeing the forgetting policy. This manager applies the decay and summary logic to ensure efficiency, privacy, and relevance. An example scenario would be a customer support agent that remembers our user preferences over several months but automatically deletes sensitive logs after 30 days to remain compliant. This architecture is what separates a simple toy app from a production ready enterprise system. It balances the need for fast working memory with the need for infinite retrieval and the practical necessity of data management. This is the blueprint for a professional cognitive system that can scale to millions of users while remaining secure and responsive. It is the gold standard for modern agentic engineering and system design. We have reached the end of our investigation, and the case is now closed. The primary takeaway today is that the future of intelligent agents is not just about having larger and larger context windows. Instead, it depends on building a robust and tiered memory architecture. By combining fast working memory for short term tasks with infinite retrieval for long term knowledge and human like forgetting mechanism, we move from building simple chatbots to building true cognitive architectures. We are moving from parrots to partners. The final thought I want you to leave with is that in the world of AI, we often trade perfect recall for flexibility, focus, and scale. A system that remembers every single word ever spoken will eventually collapse under its own weight. But a system that remembers what matters can change the world. Thank you for joining me on this deep dive into the memory systems. I hope you now have the tools and blueprints needed to start building your own intelligent partners. Remember to think about the desk, the file room, and the shredder as you design your next agentic application. Good luck with your builds, and I'll see you in the next case file. If you like this video, please do like, share, and subscribe. Thanks for watching.